Okay, welcome to the video lessons for Chapter 10, Section 7, entitled Special Segments in a Circle. Now in 10.6 we discussed secant and tangent segments in circles and their relationship to arc measure. In other words, the relationship between the angles and their intercepted arcs. In this section, we're going to be discussing tangents and secants again, but in an entirely different way. We'll be talking instead about the lengths of the pieces of those secants and tangents when they intersect in a circle. So we basically have two basic rules to talk about, one of which has a couple of different forms. And those are when two secants intersect inside of a circle, which would mean two chords intersecting inside of a circle, and when two secants intersect outside of a circle. So the first of those two rules, your book numbers Theorem 10.15 and entitled Segments of Chords Theorem. And they're really not worded all that well. It says if two chords intersect in a circle, then the products of the lengths of the chord segments are equal. So what I want you to notice is that in the picture, chords AC and DE intersect at point B. This divides each of those chords into two pieces. You have AB, AC, which is broken into part AB, which we'll label at length X, and BC, which we will label length Y. And DE is broken into two pieces as well. We will label those pieces. DB is going to be length A, and BE is going to be length B. The reason I'm doing it this way is because what this rule is stating is that the products of the pieces of those two chords must be equal. In other words, XY, so AB times BC is XY, has to equal AB, the pieces of the other chord. So in each case, the chords are being broken into two pieces, and if we multiply the lengths of those pieces together, they must be equal. So in example A, if we want to find the value of X, we are going to apply this rule. That is, AB times BC equals DB times BE. Okay, the products of the pieces are equal. So that would be 5 times 12 equals 10 times X. Okay, so we're just going to solve that equation. 5 times 12 is 60. 10 times X is 10X. And then we divide by 10, which gives us X equals 6. Okay, so on the surface, it's a relatively simple idea. Now, what most math books do is they raise the level of rigor by increasing the difficulty of the lengths of those pieces. So in example B, we would have PK times KM equals JK times KL. Again, those are the pieces of the chords. We multiply those pieces together, and that gives us an equation. So PK is quantity X plus 1. KM is quantity X plus 8. JK is quantity X plus 10. And KL is X. And that X is not very well placed. That is the length of KL. So this requires us to remember our algebra skills, because on the left we're going to have to FOIL X times X, X times 8, 1 times X, 1 times 8. And on the right we're going to have to distribute X times X and X times 10. So our next row would be X squared plus 8X plus 1X plus 8. That's our foiling, first, outer, inner, last, equals X squared plus 10X. We distribute that X. Now we do have some like terms to combine there, so we do combine 8X and 1X together in our next step, which gives us X squared plus 9X plus 8 equals X squared plus 10X. Now the solving process would involve moving all of the x's to one side, and when we do that, we subtract x squared. Well, x squared would drop out of the equation. So then we would move 9x to get it by itself by subtracting 9x from each side. And that gives us our answer, 8 equals x. So there are two more examples on the next page. Please pause the video and try them on your own, and then resume the video and see how you did. So on example 1a, we should be setting up the equation QP times PS equals TP times PR. So based on what we have here available to us, that is 6 times x equals 4 times 15. That would be 6x equals 60. Then we would divide by 6 to get x equals 10. Now 1b is a little bit more difficult than that. We have ws times sy equals zs times sx. So we plug in, that is x times quantity x plus 12 equals quantity x plus 6 times quantity x plus 2. So just like the second example on the previous page, we would need to distribute on the right side. X times x is x squared. X times 12 is 12x equals. And then we would need to FOIL on the right side. So we would do x times x, which would be x squared. X times 2 would be 2x. 6 times x would be 6x. 6 times 2 would be 12. We would then combine like terms, just like we did on the last page. 2x plus 6x is 8x. So we have x squared plus 12x equals x squared plus 8x plus 12. Then we would move the x's to one side, which involves subtracting x squared. Just like that previous example, it drops out. Subtract 8x from each side. And we get 4x equals 12. Divide by 4. And we get x equals 3. So that is our rule for when chords intersect. We simply multiply the pieces of each chord together and set them equal to each other. Now, that's what we do when they intersect inside of a circle. Now, when two secants intersect outside of a circle, your book does a very poor job of wording this rule. Essentially, we have here two secant segments, AC and AE. These are secants because they intersect the circle at 2 points. Now what we need to notice is that the secant segments are being broken into an outside portion, which would be like AB or AD, and an inside portion, BC and DE. Now we're not actually interested in the inside portion because our rule, and this is worded incredibly poorly, you can read it for yourself, but it's just not good. Our rule is very simple. It says the outside portion, which would be like AB, times the entire length of the segment, such as AC, equals the outside portion of the other segment, AD, times the entire length of the other segment, AE. That's the rule. Outside part times entire length equals outside part times entire length. So let's do the example at the bottom. Before you start, you need to think to yourself, what is the entire length of GJ? Well, that would be x plus 8. So we would write that as the quantity x plus 8. The bottom secant's a little bit easier. 10 plus 6 is a total length of 16. So when we write out our equation, we are doing the outside portion, JH, times the entire length, JG, equals the outside portion, JK, times the entire length, JL. That would be 8 times x plus 8 equals 6 times 16. When we solve that equation, we will have the value of x. So on the left side, we need to distribute the 8. That would give us 8x plus 64. On the right side, 6 times 16 is 96. That's a two-step equation, so we would subtract 64 from each side, which would give us 8x equals 32. And then we would divide by 8, which would give us x equals 4. Now, on the next page are two examples. I'd like you to pause the video and try example 3B on your own. Let's have a look here. Yes, try example 3B on your own, and that should be an X up there, so please correct that on your notes. This should say X. Okay, please try 3B, and then resume the video and see how you did. 3A is going to take more explanation, so we're going to do that one together. All right, so on 3B, again, we're going to do outside portion, TW, times the entire length, TX, equals outside portion, TY, times the entire length, TZ. Now again, we should have already thought to ourselves, well, 12 plus 7, that's 19 for the entire length, and x plus 6 is the entire length for ZT. So in our equation, we have 7 times 19 equals 6 times x plus 6. We would multiply that out, so 7 times 19 is 133. Just going to double check that real quick, make sure my mental math is not off. Good, 133. On the right side, we're going to distribute to get 6x plus 36. So we did 6 times x, 6 times 6. We then subtract 36 from each side, which gives us 97 equals 6x. The final step then would be to divide by 6. 97 is not divisible by 6, nor does the fraction 97 over 6 reduce. So I would just leave that as my answer, 97 over 6. You could convert that into a decimal, that is 16.6 repeating if the directions require. All right, let's talk about 3A now. This one's a little bit more difficult. So first of all, the entire length of the bottom secant is 9. The entire length of the top secant here is x plus 9. So on the surface, this problem doesn't look any harder. RT times RU equals RS times RV. But when we go to plug those numbers in, we have x times x plus 9 equals 4 times 9. And unlike the previous examples that we have done, when we multiply that out, we get x squared plus 9x equals 36. There's no x squared on the right side of the equation like there has been previously, meaning that this is not a linear equation. This is a quadratic equation. Now, there are three methods to solve quadratic equations that you should have learned in Algebra 1. There is solving by factoring, which may or may not be possible. There's solving using the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, which we should remember from algebra. And there's completing the square, which is much less used. Now, should always check to see if it's possible to factor. So what we should do first is move the 36, which gives us x squared plus 9x minus 36 equals 0. And then we have to check to see if this is a factorable trinomial. So this is taught a bunch of different ways, but what it boils down to is we need to see if there are numbers that multiply to negative 36 and add to positive 9. There are. Those numbers are positive 12 and negative 3. Okay? So when we're looking at the factor pairs of negative 36, we have, negative 1 and 36. Well, those add to, 35. That's not going to work. We have to work our way through all the possible factor pairs of negative 36 until we find a set that adds to positive 9. 12 times negative 3 is negative 36. 12 minus 3 is positive 9. So this is factored correctly. Now our zero factor theorem says that we have two things here, one set two set of things being multiplied together to equal 0, which means either x plus 12 equals 0 or x minus 3 equals 0. One of those two binomials must equal 0. Now, algebraically, these are both solvable equations. We would subtract 12 from each side and add 3 to each side, and that would give us possible solutions of x equals negative 12 or x equals 3. However, this is a geometry problem. X is a length, so it cannot be negative. So we throw out the possible solution x equals 12, and we keep x equals 3. I'm going to pause the video at this point, and we'll do the second half of the lesson in the second video. Thank you for your time.